Okay, everyone, this is good. I'm David Ernest from Group SWI19 here to present our project. Our project is about graph reasoning large language models for inclusive mathematics education in Uganda. Let us start. So that's our table. That's our contents for this presentation. So the background introduction. So home-based learning. That's NCD's focus, inclusive education, mathematics foundation. Like the current challenges, caregivers lack tools, abstract math, adaptive strategies, tailored lessons, household examples, disability sensitive. So our goal is to support parents and teachers, like adaptive, inclusive math learning, and then curriculum aligned. So these are our literature review related works. So as you see the paper, this one, like manage them to summarize them into models, tell the results from models, architectural limitations, the context limitations. So as you see them, we managed to get 6. These ones, as you see the models, the ChatGPT Llamas 2.7b LLMs reply. As you see the results from the models, architectural limitation and context limitation. Also, that's also another table for the literature review. Then the problem statements, the demarcation problem, like home-based learning, like challenges, like caregivers lack structured curriculum aligned guidance, inclusive education gap, learners with disabilities face insufficient support, mathematics learning, abstract concepts are difficult to teach at home. So the contribution like adaptive content generation, like AI must generate lessons, examples, and exercises tailored to learners' needs. Curriculum alignment ensure outputs allow NCDC primary math standards. Disability sensitive personalization, diverse cognitive and accessory abilities. So and should be resource constrained deployment. So research questions and objectives, like how can home-based caregivers support math learning effectively? How can AI generate adaptive curriculum-aligned content? How can teaching strategies be personalized for learners with disabilities? What is required for AI tools work offline in source constrained settings? So the objectives are to develop an AI-powered co-teaching tool to generate adaptive, inclusive curriculum-aligned math content, to incorporate disability-sensitive teaching strategies, to enable mobile offline deployment from baseline, because we wish to deploy our AI on the offline mobile application so it can be used by people at low cost. So the research contributions and outputs, we developed an LLM powered co-teaching tool, we built an adaptive learning content generator, we deployed novel graph reasoning for personalized teaching strategies. So this is our methodology architecture. So we used that's graph based retrieval adversarial fine tuning. This was the methodology employed. So as you see, self-explanatory, we started with dataset creation, and then there we created a dataset. Then we put that in a knowledge graph construction. So we use Neo4j to construct a knowledge graph, and then we put it to the coder to train, and then we use the RGCN, and then we get the embeddings, then fine tuning and reasoning. So we fine tuned it, and then after the deployment, then we deployment. There after that same validation and feedback. So we gave it to teachers, caretakers, like to give us feedback about its usability. So that's the architecture for the models. That's Llama 2B7 chart, and then Gemma 2B. So as you see are the input embeddings, the normalization, then grouped multi-query attention. That's for Llama. Then the game I use grouped query attention. Then this normalization layer. This in here the forward feed neural network, and then we will have the linear and then softmax. So here you have our mathematics foundation. The models are built on similar mathematics principles and are all based on the decoder only transform architecture. So these are These models are decoder-only transformer architecture. They all based on the decoder-only transformers. So Llama 27B and Falcon 1B are both prenorm, while Gemma is a hybrid. So transformers rely on self-attention. As you see here, this attention equation where Q stands for queries, keys, and then the values. Okay. As we continue, so there you have a multi-head attention. Like all models make use of multiple independent attention mechanism. Each head focuses on different relationship and tokens. So here this is the multi-head query function, and then you coordinate with head, and then you coordinate with the different heads. Where head I is the attention. Then you have the output projection, which is WO. So also have the grouped query attention, which is GQA. Like all models use GQA, a generation of multiple head attention that allows queries like heads in the groups. It's there to be more efficient. Have the normalization, as we see in the architecture, there was a normalization layer, like scales embeddings for each token. This is our function. You get the root mean square normalization, where G is the scaling parameter, B is the optional bias, and W is the linear transformation. So this you have the feed-forward neural network, that is FNN, whereby Llama and use a variant of LMP, that's multiple layer perceptron, which is sweet glue. And then smooth glue adds a gate for modulation of activations, allow neurons selectively amplify or suppress features. It's more flexible. So this is the FNN function, which is sweet glue, while Gamma uses the gate glue, which is whereby this is our function. So there also a linear layer that converts the final hidden state of each token into logits, which is a scores, and we also have the softmax function, which converts the logits into probabilities for each token. So at the end, the output will be the predicted token. So all these models are give a predict the next token. So that's a description of explorer data analysis. So that's an overview objective for all purpose. This dataset was created to provide a basis for generation of NCDC aligned maths content specifically directed at students with learning disabilities. So data collection method, data was extracted from papers, manuals, other relative documents concerning the NCDC curriculum and learning disabilities. Then the data structure and composition. The dataset is organized in a tabular form with each row representing any instruction unit. It consists of 13 columns, which include class, subtopic, disability type, environment, setup, teaching strategy. Here we have the data processing. The data was cleaned and standardized, removing formatting, inconsistencies, standardizing, and normalized to remove duplicates. Also, you have the data quality, which is cleaned and duplicated, so they are non-repeating values. Okay, this is one of our graphs. So this is a sample output like distribution of this strategy. This shows the most common teaching strategies. As you see here, we have the inquiry-based, the multisensory kinetics. We have the material visualization and applications. Also have the load distribution per class and the heat map for null cells. So because we created it, so there was no null cells. And then you have the results and the discussion. So disability distribution. This shows how the disabilities are distributed. This shows the non-all learners, dyslexia, HDH, dyscalculia, auto-processing disorder. As you see, so this shows that the most common disability. So the most common disability in our data set. Okay. Results and discussion. Also this distribution of teaching strategies by disability. So how the teaching strategy are distributed over the disability, a given disability. So these are the users from the training session. So the Gamma, the loss was Perplexity, Raj, Blue, L1 and Precision Score, then the Falcon Philip Beanstalk, then the Llama. So these are the 3 models we imagined are successfully fine-tuned on our dataset. So they give us these following results. So these are some of the attention mechanisms. So this is just a heat map showing the attention weights. So the diagonal line, the context of the next token being informed by that of the preceding token, the model successfully read competing inputs to produce output. So this teaching, then and mathematics, and Gaussian masks. So this proves the model from seeing relevant tokens, and also another. This was from the GEMA attention mechanism. So the vertical line to axis token give more attention to the starting tokens. So the model give more attention to the starting tokens. So almost completed that below the diagonal model unable to form meaningful relation with the prompt tokens. So this is a sign of memorization and not learning. So this was a sign of memorization and not learning. Okay. So okay, these are explanatory. So the red one represent more influence, blue less influence, and then the green neutral. So there was a more influence on which, a less influence on mathematics. So these are the different explainable results from the 2 models, that is Falcon and GEMA. Also this one for the Llama. Like here the base which words influence more prediction, like integration gradients on token embedding. So red high influence, blue low influence. As you see here, we explain why play-based learning is important in early mathematics. So this is how the model give this influence to these words. Okay, this takes us out to the limitation of the models. The GEMA 2B, the SUGRI completes 3 matrices for each forward and backward pass. So that's more computationally heavy. Then the activation is stored in memory at the full position. Arithmetics, that's 32-bit, increases storage cost. Then Falcon 1B instruct multi-core attention requires large matrices, weights for training, extra memory to store activation caches with pre-ALN. So then also Llama 2, it can only attend to fixed number of tokens, like about 4 tokens. Full fine-tuning requires huge resource requirements, large imbalance in the representation of some disabilities. So these are the solutions, like using Roller to reduce the number of trainable parameters and optimize memory, using mixed precision, that's FTP16, reducing the testing and training batches to prevent output of memory errors, releasing unused memory after every training step, using knowledgeable graphs to enhance reasoning, using cross-validation to make sure the model is trained on most of the data. Okay, then the model selection, and so we selected the Falcon 1B. or section for deployment, like it had better overall scores in relation to the rest and produced better output and influence. So it's relatively smaller when compared to the rest and consumes relatively less computational resources. So its training time is less, making it easier to retrain the model on updated data in the future. This is our pipeline, like fine-tuned model, uploaded to Hugging Face, and then the gradual up, and then user. So this shows how we deployed our model. So the key steps: fine-tuning, and then packaging, adapter weights, and configure files before deployment. The files were uploaded to Hugging Face space with the files API requirements, TXT custom 6, and then extension space with the environment in the cloud. The next, access users interact with the chatbot or the model via Gradual UI. So this is a screenshot of the Hugging Face where we loaded our files. So this was the flow user, Gradual front end, how to use a Hugging Face space backend, that's app.api transformers, that's Falcon 1 adapter and user input, so components front end, Gradual chat interface for input and output, backend, and then model executes for be in place. So here is this is the demonstration of the developed products. Flow use input. Here is the screenshot for how we try to prompt our model. So here, like, we gave it a prompt, and then this was the response from the model. So the conclusion of the feature works. So conclusion is successfully for a fine-tuned light LLM using curriculum knowledge data. The models can generate relation explanation between the degree concepts, demonstrates practical potential in AI, assisted learning, and curriculum analysis. So the future work is currently planned to enhancing more model performance, like fine-tuning more advanced models, evaluating educators, that is teachers, and then learners, and then optimizing the deployment, like use lightweight or quantitative models for faster responses. Then this is our differences we got.